Good morning, and thank you for joining us today for our presentation of Tribology 101, an introduction to the basics of tribology. My name is Sarah Tishner. I'll be hosting the event as your technical host. So a couple of housekeeping notes prior to the presentation. Everyone who has joined and been placed automatically on mute for the best recording of the presentation. And we do encourage you to, if you have questions, go ahead and type them up and write them in your questions window and submit them. We will have about a 45 minute presentation and then 10 to 15 minutes of question and answer at the end. We hope to get to all of the questions. If we don't get to your question, we will respond to you by email and follow up with you. And one last thing as well, there is an exit survey, a real quick survey, just a minute or two of your time, has 5 questions. We'd really appreciate your answer as you leave the webinar. Your information there helps us to make these webinars more useful to you. With the housekeeping out of the way, I'd like to introduce our presenter today, Dr. Steve Schaefer. Dr. Schaefer received his bachelor's degree in mechanical engineering and his master's and PhD in material science engineering from the University of California, Berkeley. He spent 22 years working to solve practical applied tribology issues at Battelle Memorial Institute for over 50 different industrial and government clients using a wide variety of custom designed and constructed Tribo test apparatus. He's been a long active in ASTM committee, the G2 erosion and wear, and on the International Wear of Materials Conference Series Steering Committee, chairing both of these committees in the recent past. With that introduction, I'd like to welcome Dr. Steve Schaefer. Take it away.
Thank you, Sarah. Good morning, audience. As Sarah said, I spent the first part of my career solving tribology problems that other people perhaps got into just because they weren't aware of the first principles of tribology, and likely that's because there are few course curricula at universities. You may get an odd lecture or two, but mechanical engineers and material scientists, only if your professor happened to be in that field did you get much more than perhaps a 1-hour lecture. So what I'd like to do today is just give some basics so that we can maybe stay out of trouble and go forward in the right direction. So for the mechanical engineer, I hope we leave you with an appreciation of the roles of material compatibility. That's very important in tribology. For the material science, who's well aware of these compatibility issues, hopefully an appreciation of the role of contact stresses stemming from both the contact geometry, alignment of the two pieces, and surface roughness. For the chemist or chemical engineer, an appreciation of how the aforementioned factors really dictate the varying functions of a lubricant. You probably know this better than most. For the physicists, an appreciation of the scaling factor from the atomic level all the way up to the macro or mega system level. I have some slides on that. And finally, electrical and software engineers, if any are on the line, even though you have maybe perhaps the best integrated circuit design and fabrication and the most elegant software code, these can both be rendered useless by fretting electrical contacts, and that's one of the wear modes we'll talk about. So with that, I'll proceed through the slides. Here's a quick outline. Give you some history of the origin or definition of tribology, both the term and the field. Talk about its encompassing fields, which are quite widespread. The fundamentals of tribology. 4 areas I'll cover today are surfaces in contact, friction, lubrication, and wear, and some concluding words. If we have time, we can take some suggestions for upcoming topics in the series. So what is tribology? Well, it comes from the Greek word tribos, meaning rubbing or to rub, and of course the suffix ology means the study of or the field of. So tribology is the study of rubbing or the study of things that rub. This includes and is often referred to as the fields of friction, lubrication, and wear. So tribology, relatively new word, certainly younger than I am. It was coined by Peter Jost. He was given the charge by the British Parliament to determine how much of the economy was wasted because people didn't apply the principles which should help them with wear and friction. He came up with a figure of something like a little over 5 million British pounds at that time, $800 million. And he asked, it wasn't too exciting to do this report, so he asked a linguist colleague of his for a title for the field or the study of the report, and his colleague came up with tribology. So, while it's a new word, it certainly is not a new field. Here's something I found in the book by Duncan Dowson, a great book, History of Tribology. About 4,500 years ago, a petroglyph of the transporting a statue of tea out of Egypt. If I look at this fellow here, in fact, I look closely at this fellow here, we see that he's the first recorded tribologist. He's actually pouring some sort of a lubricant, it's believed to be water, it could have been oil from animals as well, in front of a sledge to make it easier to slide the statue. So that's the first guy, but other documentation doesn't exist. A more famous tribologist from 500 years ago was the great inventor Leonardo da Vinci. And while he didn't publish his work in a technical journal, a refereed journal, he did leave some very good notes. And if we look here, we see some of his sketchings from his notebooks are indeed tests that are used to this very day. There's the ball test geometry and the sled friction test. He also designed a ball bearing. To this day, there are 5 ASTM standards. In fact, there are more dealing with the 4-ball test geometry. There's one for coefficient of friction, 2 different extreme pressure, one for grease, one for liquid lubricant. Same with wear. His sled friction is an ASTM standard 1894, the static and kinetic coefficients of friction of plastic film and sheeting. Leonardo made 2 observations. One is that the contact areas have no effect on friction. This is what he observed. And if the load of an object is doubled, its friction will also be doubled. And these are observations still made today, and we understand a little bit more why he made these. So with that, I'll talk about the applications in fields which encompass modern tribology, and they're quite diverse. And I'm going to talk about scaling factors in the next few slides. I'll talk about individual components, how these components can make up assemblies or just products, manufacturing processes, construction, exploration, and then the best example we have of scaling factors are natural phenomena. Okay. Individual components are things like gears, bearings, brake and clutch pads. And when we take these, they get both friction as well as anti-friction, and wear is important. In some cases you want friction, in some cases you want no friction. You can take these components and build assemblies, such as engines or a pocket watch, or products themselves can have very distinct tribological applications. We want very high friction if we have rock climbing shoes. We want very low friction if we're designing and constructing curving stones. Manufacturing, again, the size scale from very large rolling mills, stamping presses, smaller scale turning, grinding and polishing. We have wear and friction as important phenomena. And making of mirrors and making of very, very small lenses. All of these are manufacturing processes using tribology in a useful way, particularly grinding and polishing. That's a controlled wear method. In the construction or exploration area, when we transport slurry from mines, there's a lot of erosion happening in the mine pumps. Very large pieces of equipment can be placed out of service because of just 10% of the entire mass is worn, but it doesn't function anymore. When we talk about abrasive wear, we have an excavator which is experiencing 3-body wear, so we have loose pieces because of the wear. Or the channel digging drill is 2-body wear, where we're just grinding into rock and there are no loose pieces initially in contact. And of course, on the exploration end, we have exploring the earth itself, drilling equipment, there's a lot of tribology going on there, and exploring space. The space shuttle is a great example of things that work necessarily on Earth, where we have oxygen and water vapor present, may not work in space in the high vacuum. Natural phenomena is a good example of the scale of wear, and friction. We look at wear, we might have erosion by water, erosion by wind. You see in that left-hand image the Grand Canyon. Many of you have visited here. And on the Sphinx, you can see the lower portion is being systematically worn or selectively worn. The harder layers by the windblown sand are remaining, and the softer layers are being worn away. Of course, it's quite beautiful, as many things in nature. When we talk about natural phenomena of friction, we get to the nano level or micro level, and it's being studied in great detail lately of the gecko feet, where there are little fibrils on the gecko feet can be turned on and off to cause it to be able to walk upside down on the ceiling, up walls, anywhere it wants, but yet let go at a moment's notice. Another area, a very small scale, is the super hydrophobicity of the lotus leaf. And this is both a chemical and a structural element. With small bumps, being wax covered, and you can see the wetting angle of water very, very high on a lotus leaf and an artificial lotus leaf. At the mega scale, we have an interesting application in tribology. Known as stick slip, and this is in plate tectonics. When you have two plates having a force building up stresses, eventually they will slip and then cause what we can record as an earthquake. And that's happening along this interface here. Normally we see stick slip in a more regular fashion, and it has to do with the compliance of the machine and of the parts. It does happen in the roof itself. So in parallel to these different scales, there are many areas of engineering and industry which have a need to use or understand tribology. We show a list of quite a few of these. I can't go into all of them, but the webinar will be available later. You can imagine aerospace, I mentioned that, the space shuttle, agriculture, digging equipment. The automobile is a great tribology study instrument with high temperature and exhaust gases in the engine. Brakes and clutches, of course, where we have controlled friction. And the making of the automobiles, tooling, machining, sheet metal forming. People who provide coatings provide both low friction coatings, wear-resistant coatings. Wear-resistant coatings have another subcategory themselves of thin films or thick, weld-applied or spray-applied hard facings. All of these are designed for wear resistance. In the cosmetics and personal care industry, there's tribology studies going on shampoo, on conditioner, on skin cream, how that feels, how that works. Dental implants, grinding of teeth is an important tribological study, and grinding of artificial teeth or replacement teeth is going on. And the fields really go on and on and on. And I guess the last one, university and educators, I would hope joint mechanical engineering, material science, physics, and chemistry, interdepartmental courses or lab courses could be developed to give all of these engineers and scientists an appreciation for tribology in the future. So while it's in virtually every area of engineering and science that we can think of, what is the commonality in tribology? All these diverse fields, what do they have in common? And what do we need to think about as engineers and scientists when we design products or friction and wear experiments? The commonality for all of these applications is that they have surfaces in contact and relative motion. Motion could be sliding, could be rolling, could be impacting. So we really need to then think about surfaces in contact, and that's what a tribologist really needs to consider. So let's begin by taking a little bit closer look at a surface. So what do we have on the surface? Well, first of all, it's not simple. Mostly, mechanical engineers look up bulk properties or handbook values, and this is our main surface. So steel has a certain hardness or strength depending on the heat treatment and the type of steel. And on top of this is a layer of disturbed material, I call it, and that's from the manufacturing process or handling process or even prior rubbing. On top of the disturbed material, we have an oxide. On top of that, adsorbed contaminants, at least on Earth, there's absorbed contaminants. And you may or may not have a lubricant on top of that. So the surface is quite simple. These layers all play a role, even though their length scales are quite different. The bulk properties, or the substrate material, as it were, is on the millimeter to centimeter scale. All those things on top, which affect the friction and the wear, are on the order of nanometers to microns, quite thin. So while it's not simple, it's also not flat. On top of these, or underneath all these layers, all engineering surfaces have a roughness, and that roughness is going to play an important role in tribology. And again, it comes from all prior history of the part, from manufacturing, handling, and prior use in an application. So we need to think about two aspects of a surface as tribologists. There's the physical aspect and the chemical aspect. So for physical, we might restrict that to surface roughness. There's a little bit more to that, but the surface roughness certainly dictates the contact area, and by that I mean the real area of contact as opposed to the apparent area of contact. And these would be the asperities that touch when two surfaces are placed in contact. And this is about 1/10,000th or so the true area of contact, unless the forces are very high, the pressure is very high, and the material is very elastically deforming. So we find sometimes in polymers, contact area no longer grows proportionally to the normal force, but it starts to slow down as we saturate the contact. So that's an important thing to think about. And this all dictates the contact stresses. And surface roughness also serves as a path for lubricants or reservoirs. So here's an example on the right here of two different surfaces. There's a ground surface where you can see the delay of the grinding or the directionality of it. And on top of that is even smaller micro roughness. Lower is a bead blasted or more random surface. So this is what we think about when we think about surfaces, paths or reservoirs for lubricant or debris in the contact area. On the chemical end, we want to talk about or think about the intervening layers. And these layers provide chemical compatibility or incompatibility, might be a better thing. We worry about the shear strength of these layers. It's certainly easier to shear a boundary film than it is metal. And lubricant properties, viscosity, if you have a thick enough film, we worry about that. And sometimes we can characterize these using techniques such as infrared or Raman. There's a variety of techniques available for the chemical aspect. There's a variety of methods, again, for both these. For physical characterization, we would like to characterize the roughness. Macro level, you might use a coordinate measuring machine, the CMM, to look at the waviness and form. These are the larger scale roughnesses, but they dictate macro contact stresses. In the micro area, we really want to know something about the surface roughness because these dictate the local stresses where you can have nominally very small stress on the macro level, but locally you will exceed the yield stress in many cases. So this can be measured with stylus profilometry, which is a contact type measurement method. Optical profilometers, which are non-contact. Atomic force microscopes, similar to a stylus profilometer, a bit more sophisticated. They work at the submicron level. We also want to characterize the hardness in terms of either an indent or a scratch. These all help us understand the properties of the two materials coming in contact, the two surfaces. On the chemical end, we can use infrared, XPS, X-ray photospectroscopy, Raman, Auger. We can also use viscometry to study the lubricant shear properties. So again, physical and chemical characterization help us understand the surface. So I can summarize the surfaces in contact here. We want to know that tribal forces are dictated by the interaction of asperities. These asperities have mechanical and chemical properties. Methods exist to characterize these properties. The asperity geometry and distribution result from manufacturing method, handling, and prior rubbing history. So let's move on to our friction fundamentals. Conceptually, there's actually official definitions for both friction and wear in ASTM standard G40, but conceptually, friction is a resistance to relative motion between two bodies in contact. And what happens with these bodies in contact? Where they touch, there's forces between them. And these forces can be split up into microscopic forces of molecular adhesion, which are electrostatic, or van der Waals, or metallic bonds, or microscopic forces of mechanical abrasion. And abrasion includes elastic and plastic deformation. And this will play a role in wear as well as friction. So where does friction come from? Well, remember, in addition to the chemical and physical properties, there's also contaminants at the interface. These we showed before are the oxides, absorb films and gases or foreign or domestic particles. So all of these contribute to the friction. So the coefficient of friction, COF, is a concept. It's a simple constant of proportionality. Or is it a simple constant of proportionality? The relation itself is very simple. F, the frictional force resisting motion, is seen to be proportional by the coefficient U times N, the normal force. U equals F over N, the coefficient of friction. So really all I need to do to measure it is apply a known N and measure the F. It's not so simple. Suppose a coefficient of a colleague wants to know, what's the coefficient of friction of steel? Well, I might answer, dear colleague, you can use from 0.1 to 0.6. Take your pick. that close enough for your needs? Well, not really. I kind of need to know it better. Well, then I guess we'll have to know a bit more information. Here's what we need to know, and this is just the start of a typical conversation. All right, dear colleague, what is the steel? Is it a stainless steel, 304 or 316? Is it a 400 series or a hardened 17.4 pH or the like? Is it carbon steel? If so, is it perlitic or martensitic in microstructure? Is it a tool steel? Colleague, well, I need to use it in water, so stainless steel, I guess. What is the function? What is the mechanism you're designing? I'm designing a gear-driven mechanism, and I need to size the motor. Assuming some frictional loss in the gears, I need the coefficient of friction for this. Gears. Then I guess it needs to be hardened. How about the driven gear? What's its material? Same, I suppose. Well, I'm not sure that's a good idea, depending on the contact stress, sliding velocity, and surface finish. Do you know these parameters yet? Well, not yet. I'll probably use standard values for my gear design handbook. Okay, I gather you need low friction. How about a lubricant or use of a lubricious coating? Are these permitted in the design? Oh, I didn't think about that. Well, coating is probably okay, but I don't think liquid lubricant is permitted in this application. All right, settle on a coating. Okay, how long will it need to last? Well, obviously for the lifetime of the mechanism. Can't you just tell me the coefficient of friction? Well, dear colleague, really I need a bit more information because I'll likely need to run a test depending on how precisely you need the coefficient of friction. So this is sort of the conversation you have when somebody is needing the coefficient of friction and hasn't thought in advance about all of the factors that go into it or even their application. So all things considered, the coefficient of friction appears somewhat complicated. Surface roughness will play a role, lubricant plays a role, surface chemistry plays a role, contact stress plays a role, contact geometry, environment, temperature, sliding speed, sliding direction, duty cycle, whether it's continuous or start-stop, whether it's in the same direction or reversing. All of these things play a role. So the coefficient of friction is somewhat complicated. All things considered, it's not so bad after all. While it appears complicated, it's relatively easy to measure. Again, we only need two things, the normal load and the friction force, and we have to measure it in the right conditions. I can summarize now the friction fundamentals. Again, the equation is simple, but measuring it correctly really requires some care. When assessing a system's tribology needs, we must consider the materials, whether there's a coating, whether there's a lubricant, the contact area, the geometry, the contact stress, the surface roughness, the sliding speed, the sliding mode, the duty cycle, whether it's continuous or intermittent, the environment, temperature, humidity, and the atmosphere. Is it air? Is it exhaust gases? Is it vacuum? So the one thing I'd like to leave you with today to always think about, my dear colleague, friction is not a material property. You can't look it up in the handbook. Friction is a system property. There's no such thing as the coefficient of friction of steel or the coefficient of friction of rubber. You might be able to look up the coefficient of friction of steel on copper or steel against steel. But again, as we saw in the previous slide, there's a lot more to it than that. You need to know the environment, you need to know the contact stresses, you need to know a lot of things to get it right in your design application. Let's talk about lubrication for a few minutes. What is the function or the role of a lubricant? Well, there are four primary roles: to reduce friction, to prevent or minimize wear, to transport debris away from the interface. That's why many lubricant systems have filters on them, and to provide some coolant. When we look at or think about lubrication with liquid present, we can think in terms of lubrication regimes. So really, people have decided regimes can be based on fluid film thickness. It's a very simple analogy. There's a factor called the lambda ratio. The lambda ratio is defined as the ratio of the fluid film thickness, which can be measured or calculated, to the composite surface roughness. And that can certainly be measured much more easily. Composite roughness, you can see down here, is made up of the root mean square roughness of surface 1 squared plus the root mean squared roughness of surface 2 squared of that. That's the composite surface roughness. So in between this roughness, there's a layer of liquid lubricant. If this lambda ratio, the ratio of that liquid thickness, film thickness, to the composite roughness is greater than 3, roughly, we have what's termed full film or thick film lubrication. This is the field of hydrodynamics. In this case, the surfaces are separated completely, and merely the shearing properties of the lubricant are what determine coefficient of friction. In the middle range, between lambda of 1.2 and 3, we talk about mixed or thin film lubrication. And now in the thin film region, we're starting to get contact between the asperities, but we've still got some support from the lubricant itself because of the pressure built up in the interface. But we're starting to see a lot more contribution from the asperities or what's on the asperities at the boundary film. And finally, when we get to lambda of less than 1.2, roughly, we're in boundary lubrication. This means we're sliding asperity on asperity, and we're either shearing a low shear stress film on the asperities, which is a boundary film, or we're shearing the material itself, and maybe we've been plucking pieces of one material off of another. So when we get lubrication too thin, or the absence of lubrication, we're in the boundary region, or what's might be known as dry lubrication, which is a bit of an odd. These regimes have been described on the Stribeck curve, or my German colleague tells me the Stribeck curve. And if I look here, I've plotted coefficient of friction in 4 orders of magnitude, and what's called a Kersey number, or speed times velocity divided by load. So if we look at the 3 regimes we just talked about, thick film, thin film, or mixed, and boundary, which is really the absence of any support by the lubricant, we think about how these were generated. And this blue curve shows us the coefficient of friction ranging from 0.1 to 0.001 or 0.003 or so in the hydrodynamic region, or thick film, out here. In the complete absence of boundary lubricants, the coefficient of friction can raise to values almost to 1. And in fact, in very clean environments like vacuum, clean surfaces, well over 1 has been established by Buckley at NASA in some high vacuum experiments at copper and copper. Well, the Stribeck curve just simply was the geometry of a journal bearing in rotation. The fluid is trapped in the interface and builds up a pressure as it gets into the converging gap. And actually, if it's going fast enough, with a high enough viscosity and a low enough load, that at this region, we're getting to the higher end, and you can actually float that journal on the within the lubricant film, and we have very, very low friction. If we go to lower speeds and viscosities or higher loads, we move this way, and again, we start to make asperity contact here. We get more and more asperity contact, so our coefficient of friction is rising by 1 or 2 orders of magnitude, and finally, we have full asperity contact when the journal is going either so slow or the load is so high, or the viscosity is so low, it can no longer be supported in this high pressure region at the bottom here, and get touching. And that's why start-stop, where your speed is low, is so damaging in automobile journal bearings, because now we're touching. This is why the chemist must put additives in the lubricant to deal with this boundary region, to keep it down here for that short time before we build up the hydrostatic pressure, hydrodynamic pressure. There's also boundary lubrication provided by solid lubricants. We finish with liquid lubricants. And solid lubricants are compounds with low shear stresses, because we're going to be shearing these, and they're protecting the metal surface underneath. And these tend to be hexagonal or layer compounds like molybdenum disulfide or moly disulfide, graphite, tungsten disulfide, hexagonal boron nitride. All of these have a crystal structure like this, and they talk about behavior like a deck of cards for simplicity. So we shear easily along what are called the basal planes, not so much here, and these platelets would smear out, protecting the surface, and so all the shear takes place within the solid lubricant. The other type of solid lubricant are known as bonded films. So these might be diamond-like carbon under the right circumstances. If you look in the literature, diamond-like carbon has been shown to have coefficients of friction as low as 0.01 in certain circumstances, very controlled circumstances, but you'll also find it, depending on the application, as high as 0.6 to 0.8. So it can be low friction depending on the application. We also have resin-bonded films with PTFE or Teflon inside of them, or other slippery particles. These may be baked on, and therefore may have a temperature limit at which they can be applied. We also have impregnated porous anodizing. Again, we can either put an oil or slippery particles in this anodizing. So it's a little bit different And the resin bonding, but again, we're attaching to the surface some slippery material that serves as a sacrificial layer. That's really what we mean by a solid lubricant. If I could summarize now these lubrication fundamentals, we've got key factors of fluid shear properties, chemistry, and thermal conductivity or heat capacity. I didn't mention that too much, but we need to take the heat away from the sliding interface. So in the fluid properties, we've got the viscosity and viscosity index, or how it changes with shear rate. We also have the pressure viscosity index. We've got chemistry then of the lubricant in addition to the shear properties. Its reactivity with the surface. Some lubricants are not very well good at lubricating some metals because they don't react with that metal. Could be because it has particular oxide on it. So our chemist friends need to develop additive packages to make that lubricant reactive with the surface, so we form a boundary. The extreme pressure constituents, so that when we do have contact, we don't get metal-to-metal welds or plastic-to-plastic welds or plastic-to-metal welds, which is an adhesive wear mode. We'll cover that in the next section. And finally, the shear strength of solid lubricant coating, that's a key factor in this lubricant's effectiveness. Let's talk about wear. Again, the conceptual definition is the removal, or I'm going to add displacement of material, because even if you haven't removed it, the changing geometry, if you push material around or drag it around, could change the functionality of it. So if you remove or displace material from one body when subjected to contact and relative motion by another, you'll generally end up with wear. I'll talk in this section about 6 primary wear modes. There are other modes. There are sub-modes of these modes, but we have abrasive wear or scratching, adhesive wear, galling or scuffing, sometimes referred to, fretting or fretting corrosion. We've got erosion, erosive wear via cavitation or impact or electro arcing, rolling contact fatigue, which results in spalling or delamination, and finally Tribo corrosion, where corrosion plays a role in the wear. So I'll go through some quick examples of these. Maybe some you'll recognize. Abrasive wear is known as scratching, and the key here is the harder material scratches the softer material. And the micrograph there shows one pass of an asperity, a control asperity, over the ground surface. You can see the lay of the grinding marks below it. And what you notice here is the shear lifts or the displacement. And you can imagine the next asperity that comes by off-center or next to it. These shear lifts will be taken off and taken out of the system or ground back into the system, and so they're being lost because of subsequent contact with parallel or non-parallel asperities. And you can imagine, again, changing the direction. If I go across it, I'll take off quite a bit more than if I go next to it, perhaps. Adhesive wear, known as sometimes galling in the extreme or scuffing, it begins as local welding. So at the asperity contact, we no longer protected by our boundary film. We get a small junction forming. That junction builds up because there's no escape. And suddenly you get a very big pileup, and that drags across the surface, as we see here in these stainless steel examples. Great amounts of displaced material known as galling. So here material compatibility is important for adhesive wear. We really want incompatibility, so they don't have an affinity to bond or locally weld to one another. And that's all affected by stacking fault energy, crystal structure, natural oxide formation, all of these things. Fretting or fretting corrosion is defined as small amplitude displacement, less than 50 microns. So experiments in this regime or real situations generally have zones of no slip and slip. And you can see in the center here the zone of no slip and then the boundary around it of slip, and this is wear debris that's built up around the interface. So we again start with small adhesive pull-outs occurring at the boundary between the slip and the no slip. Often these will oxidize, so sometimes referred to as fretting corrosion. The fundamental studies have been done showing this also occurred on noble metals, such as gold. So it doesn't require corrosion, but it's almost always the case in normal circumstances. Erosive wear can be caused by cavitation or impact, basically of particles or gas bubbles collapsing in the case of cavitation. In electro-arcing, we have, it's also known as fluting damage. Down here you can see a spark has jumped because of poor grounding. This is the race of a rolling element bearing. And you'll see this sometimes because, again, of poor grounding, the solution to this is just better grounding. You get a spark jumping across the bearing. Here's the classic erosion curve of these are ductile metals and these are brittle metals. And so you can see that the maximum in erosion rate for brittle metals occurs at 90 degrees. This is the angle of impingement. The maximum for ductile metals occurs, or ductile materials occurs at 18 degrees or so. So this is why rubber works very well in case of a mask for grit blasting, because it's very it's very ductile. And steel does not work as a particularly good mask for ceramic because they're in the highest angle of impact. Grit blasting is at 90 degrees. So there's a dependency in all these on particle shape, size, composition, angle of impingement, again, the ductility of the target. In the case of cavitation, now we've got bubbles collapsing as they might make their way through into a low pressure region. And this can happen on ship propellers and past valves. And here's a steam control valve where a rapid stream went through, the pressure dropped on the other side, and cavitation. Rolling contact fatigue, we end up with spalling or delamination. And this is a result of reversing subsurface shear stresses each time the roller or ball passes over the surface. You get an accumulation of these stresses, and you get a subsurface fatigue crack formation, generally at a microstructural inhomogeneity like an inclusion. And in fact, you don't see much short rolling contact fatigue failures anymore now that they've done a much cleaner steels such as vacuum induction melted and vacuum arc remelted. Vim bar steels. Almost every rolling element bearing now is made from Vim bar type steels. Essentially, a crack will initiate at the surface, below the surface at some inhomogeneity. It will go towards the surface, and then you can see here, this is about to spall out. And this is the result. You have a spall and an inner bearing race. What happens then is the debris, as a result of this, typically gets caught in the interface or in the bearing and gets rolled over, and that creates additional damage. So once it starts, it rapidly accelerates. In tribal corrosion, we have wear in the presence of corrosion, and these can have a synergistic effect. You may have formed a passive film on an object, but in the presence of tribology or wear, you wear off this passive film, which then has to reform, and it wears off again, and it goes on and on. So this can happen with both erosion or sliding wear. Two important areas where tribal corrosion takes place are biotribal corrosion, and we see a hip implant here, and that's an area where we have rubbing in the presence of an electrolyte. Also, downhole drilling is an environment, another environment where tribal corrosion takes place. There's actually a guide, an ASTM guide for determining the synergism between wear and corrosion by measuring them separately and together and determining the effects, synergistic effects. How do we assess wear? Well, in recent times, the concept of the wear coefficient was presented by Archer. We've modified it more recently to take out a hardness so that it actually does have dimensions. The dimensions are the volume of material removed per unit load and sliding distance. So this would be millimeters cubed per Newton meter. So we remove so many cubic millimeters of material after sliding under a load of X newtons for a distance of N meters. And I often see people reduce this because I've got length here and length here to millimeters squared per Newton or 1 over kilopascals. But please don't do that. It has no physical meaning. This does. I know how much was removed, how far I slid, and what the load was. And once we get K, we can use it to predict component lifetimes, providing the Tribo system doesn't change wear modes. So if I have a value for K here, and I measured it in a 2-hour test, it's a small amount. Somebody wants to know if this material, this interface will last 5 years. As long as the wear mode doesn't change, I can multiply my 2-hour test by the factor that gives me 5 years of sliding under the same load, calculate the volume of material removed, and then determine by the design criteria whether it's still a functional interface. Again, as long as I don't change the wear mode, I'm okay. So duty cycle and directionality can also influence wear. Start-stop can be much more damaging than continuous motion, so we might want to run a start-stop or a reversing test because unidirectional sliding is very different from reciprocating sliding. So these are things we need to consider in our wear experiments. If I could summarize the wear fundamentals, well, like friction, wear is a system property, not a materials property. You can look up wear rates for very well-characterized systems, but in other cases, you really need to measure it in order to apply it to your system if it's not as well-characterized as one you might find in the literature. There are several distinct wear regimes, though sometimes they can operate simultaneously or sequentially. So you'll often observe what you think is abrasive wear, but that results from initial adhesive wear. But again, once the adhesion took place, particles broke loose, they were trapped in the interface, and it leads to abrasive wear. So if you've properly simulated the system in wear mode, the wear coefficient can be used to predict lifetimes. So a few final words. I think we're on schedule here, so we can handle some questions for today's seminar. Key concepts I think I'd like to leave you with is that coefficient of friction is a material property, is not a material property, it's a system property. We need to really simulate the system if we want to get the coefficient of friction right. We're only measuring two things, normal force, applied normal force, and frictional force, but you have to have the system correct. The wear rate, or wear resistance, again, depends on the wear mode, which is a function of the Tribo system. So we need to get that Tribo system defined properly. Finally, if we properly characterize and understand the Tribo system, the odds are much better that we will succeed. So we can make the right choice for materials, contact geometry, and chemistry, and make the appropriate measurements to give us the answers we seek for our design. I'd like to give you a couple of means to assess or think about assessing Tribo systems. And these are instruments provided by Bruker. One is our universal platform for tribology studies, where two surfaces meet. This is our UMT, Universal Materials Tester. It can cover a large load range. We saw that's important. A wide variety of environments, corrosion, high temperature, liquid, low temperature, and a wide variety of configurations, both rotating and translating motions. And you can see all these configurations can be done on a single machine here. We can do many different tests. We have linear stages. We have high-speed reciprocating linear drives. We can do threading tests. We have a block-on-ring test. That's an ASTM standard. We have rotary drives. So again, all these different geometries can be done. And finally, at the micro scale and nano scale, indentation and scratch testing can be done by just changing the head up here. We can cover a large load range, both in the nano and micro regime, a wide variety of imaging options, atomic force microscopy, profilers, and optical microscopy after we've made the scratch or indentation can be covered. And with that, I believe I can wrap up and on time and open the floor to any questions.
Thank you, Dr. Schaefer. Hello, everybody. I am Suresh Query. I will help organize the question session now. There are several questions from the audience. I have grouped them so that most of these will be answered in the time, available time. First question is very interesting. All these questions are very interesting, and first one came as we are dealing with polymers, typically membrane applications. These polymers are for membrane applications. Can you comment on the role of tribology for testing of membrane?
Okay, the question is comments on the role of tribology for testing of membranes, and the membranes are polymer membranes.
Right.
Certainly there is a role of tribology. I would have to say that this is an area when you get to these soft membranes or thin films where we use very, very low loads to measure these effects, then we start to get into the stiction, the AFM type measurements. And I would say the challenge there is in establishing the contact between the membrane, you're trying to measure its properties, and the tip or the material tip of the probe, whether it be an indenter or an AFM probe. And the challenge again is getting a probe made of a representative material. There are well-characterized materials, silicon oxide or some metals or diamond, but if that is not the contact of interest, then we have to try and simulate it with something else. So it is important, and it is very challenging, and I guess I have some colleagues here with me who may be more versed in membrane testing. My testing career was more on the heavier end, but the answer is yes, it is important, and I believe we need to simulate the contact not just the geometry but the material of interest in order to properly simulate the tribology of membranes.
Thank you. There is another question, very interesting. Can COF be more than 1? That is coefficient of friction, can it be more than 1?
Yes, oh yes. I think the examples many of us are familiar with, and the reason is adhesion. Certainly with abrasion and such, it's hard to get above 1, but adhesion gives us that capability. And because now we're trying to break very, very strong bonds. One example, I think, where they try to get above 1 is in the tackiness of race car tires. So that's something people can see in the real world. Other examples, I think I mentioned earlier, in the experiments done at NASA by Buckley in high vacuum with very clean surfaces, copper, for example. One block of copper was placed on another under its own weight only, but having cleaned the surfaces in vacuum so there's no oxide, they basically welded together, and I think coefficients of friction were up to 10, which is certainly greater than 1. But under normal circumstances in real life with a lot of contaminants on there, that tends to prevent such significant welding. But it is possible to have a COF greater than 1 under certain circumstances.
Okay, thank you. Why is it important to match geometry if the materials are correct and the phase is correct? That shape matters.
Suresh, please, once again.
Okay, why is it important to match geometry? I think the audience is trying to talk about the conformal context and things like that. If the materials are correct and the film is correct, that shape matters.
Okay. Well, I can give a couple examples. The first is when we talk about flat-on-flat sliding where galling is a possibility and we're trying to establish a galling threshold. And a lot of work has been done in this area. If I have a flat contact against a flat contact at the right contact stress, when I form small junctions, these junctions can grow and shear off, and there may be no place for them to go because I'm flat on flat. They're trapped in the interface. They continue to grow, and eventually they rip out and then cause significant additional damage. You can picture the same example with a sphere against a flat. So now I have point contact, and while I may have the ability to create a very, very high stress with a small load, I don't have the same ability to trap junctions in the interface because it's really only a very small point, and they may break before they can grow to a critical size and shear off as a large particle and be trapped in the interface. So in that case, flat on flat is very difficult to simulate if we're looking at galling characteristics with a point contact. It really does need to be flat contact.
Next one. What are the best ways of determining or calculating what lubrication mode a system is operating in?
I'm sorry, what mode?
What are the best ways of determining or calculating at what lubrication mode a system is operating in? I think,
yeah, but what lubrication mode? That's a hard one. Film thickness calculations can be made. That's about the best defined area of tribology is liquid lubrication. And there are programs, I believe, online if you know the viscosity properties. And again, it's for a very specific geometry of most likely journal bearing. So if I know the viscosity properties, the load, and the temperature, these have been well established. In fact, well over 100 years ago, I believe Reynolds did this perhaps as part of his studies, calculating the film thickness in a journal bearing. In other situations, it is much harder. And I think the safe assumption is it's probably operating in mixed film or boundary. You really need a very confining geometry in order to calculate the film thickness and build up that pressure.
Next one is, which is the most important parameter to get the friction measurement right?
Oh, that's a challenging one because, as I said, that certainly depends. It's a great tribology question because every tribology answer begins with that depends. And really, I can't answer that fairly. That's like saying choose a winner in a baby contest, or asking a mother which child she might love most. But in my mind, if I know I've got the representative materials and environment, I like to think about the contact geometry, just as our previous questioner asked, to make sure we're getting those interface conditions correct. But that doesn't mean that other parameters aren't important. But what I like to do is make sure I've got that contact geometry right first, and then go down my list of duty cycle, reciprocating, or unidirectional. Those are the second and third most. Again, it's impossible to answer that because it will depend on the circumstances.
Okay, the next one, very nice. This is in different area. Any advice or suggestions for personal care and skin field applications such as a lotion or cream? Testing of all these probably.
Okay, I'm glad you didn't ask me about using them. You asked me about testing. This is an area that's been done. There's a lot of work been done in this area, and again, it gets more into the micro and nano region because the things we are testing, such as hair, for example, are very, very small, on the order of maybe 100 microns across. So we need a very small probe, and we can sample the effect of application of various shampoos or conditioners on the either the indentation or the scratch properties of hairs. And again, so that would be very small loads using micro systems or nano systems. The work that's been done, to my knowledge, on skin, again, with very, very small probes, looking at the resilience or the indentation response and load displacement response of skin. These are the areas of micro and nano tribology with very light loads, and looking at load displacement or scratch resistance can be applied.
Okay. We can still take maybe a couple of more questions, maybe 3 or 4 of them. The next one in this is the importance of surface roughness on the impact wear. What is the importance of surface roughness on the impact type of wear?
On impact wear?
Mm-hmm.
Okay. I have to think about this for a second from first principles. I'm guessing that depending on the impacting particles, first of all, the higher the surface roughness, I would have to say the higher the local contact stress, because the impacts may not be shared over as large a surface if they're just hitting the tips of the asperities in the surface roughness. But I think as they wear down, as the material is removed, impact wear probably becomes less dependent on the initial surface roughness because you develop the surface roughness as a result of the impacts, and therefore the initial surface roughness is no longer present. It's created its own roughness. So that's my thoughts on that.
And there is another very interesting question. This is, why are there so many different ASTM methods related to tribology?
Well, again, tribology is not a simple area. Some of these methods are assessing the lubricant EP, or extreme pressure characteristics of a lubricant, both liquid and grease. Some are assessing the boundary lubrication or film forming properties of a grease or liquid. Some are assessing just the material properties themselves, two materials in contact. So the ASTM tests are designed to simulate some or approximate some real-life situation, like the G98 galling test was to approximate a fastener or a nut on a threaded bolt, as it were. We get galling propensity in this type of an arrangement where I've got our rotating sliding. Other tests look at abrasion, so that's a different wear mode. So you might have the dry sand rubber wheel abrasion test, G65, which is a 3-body test, or you might have what's known as the tabular abrasor test where now my particles are incorporated in rubber wheels and I've got two-body abrasion. So each of the ASTM tests is attempting to simulate a different wear mode or a different frictional characteristic. So we're trying to distill these down to the interface or something like this.
Okay, thank you. I think we still have 3 more minutes. We can take another question, maybe short one. Are there any ASTM standards for measuring the coefficient of friction for orthopedic application? For example, polymer on metal or metal on polymer, cartilage on metal.
I am not aware of a specific standard. There may be. That doesn't mean there isn't. I'm not aware of a specific one. What we showed earlier, the sled friction test is for a polymer film, metal on a polymer film. But again, you want to simulate these in the correct environment. So my understanding is these tests are pretty complicated to get all that environment correct and the solution. But I'm going to have to defer and get back to that questionnaire. If we have their contact information, I can certainly check and determine if there's a test design for these biomedical applications.
Okay, thank you, Dr. Steve Schaefer. I think we'll close this session here with the note. We almost came to the end of this question answer session. Some questions, there are many of them actually, and those could not be answered due to time constraint. We will get back to those soon by email. On behalf of Bruker webinar team, I thank you all once again for joining TNT webinar on Tribology 101, Basics of Tribology. Please fill out the exit survey. We will follow after the end of the seminar. We look forward to see you again in our next webinar. Thank you.